Hello students. So our next topic is angle of contact. Angle of contact is a very simple topic which you can very well understand by help of these two diagrams. First, let's have a look at the definition. It is the angle between the tangents drawn to the free surface of the liquid and the surface of the solid at the point of contact, and it should be measured inside the liquid. So when we talk of angle, obviously it is angle between two lines. The first line is nothing but the surface of the solid. Okay. And the second line will be the tangent which you are supposed to draw to the surface of the liquid. And when you measure the angle between two lines, it should be within the liquid, inside the liquid. Okay, that will give you the angle of contact. So let me first explain you with the help of water. In this vessel, we have liquid water. Okay, you know, for water, the shape of the meniscus will be like this. It will be rising upward because of strong adhesive forces at the end. Now, I'll draw those two lines. Okay, first line is the free surface of the liquid and tangent to it. Correct? So, this is the free surface of liquid, and I will be drawing a tangent to this. Okay, so I have drawn a tangent to this free surface of liquid. Second line is the surface of the solid. So this is our solid part. I'll be drawing this line. This is the surface of the solid. So we got two lines, correct? Now we are supposed to find the angle. Four angles you can see. 1, 2, 3, and here also 4. So here it becomes important that we are supposed to measure the angle inside the liquid. Okay, so inside the liquid, this is that angle which will be denoted by theta. This is the angle of contact in case of solid and liquid like water. Clear? Secondly, let's move on to another liquid. This is considered as mercury. Okay, you know, for mercury, the meniscus would be like this. Because of strong cohesive force, the meniscus will drop like this. Correct? Now again, I'll draw two lines. First line will be tangent to the free surface of liquid, which I'm drawing like this. This is the tangent to the free surface of the liquid. Second line will be the surface of the solid. So let us consider this is our surface of the solid. Clear? Again, you can see four angles. 1, 2, 3, and here also 4. Now, which one to select? It should be selected within the liquid. So, inside liquid part, I'll be having this angle. Is it clear? So, angle of contact in water, angle of contact in case of mercury. What is the conclusion? Angle of contact in case of water will be acute, whereas in case of mercury, it will be obtuse, greater than 90 degree. Okay. In general, I can say liquid which wets the solid, a liquid which wets the solid has an acute angle of contact, whereas a liquid which does not wet the solid has an obtuse angle of contact. Our next topic is shape of meniscus. We have seen we have concave shape, we have convex shape, we have completely flat plane. Actually, it depends on your view. In when you view it from the top, okay, and if you see such kind of shape, okay, then from top it will be termed as concave meniscus. If you are again at the top, you are supposed to view it always from the top. And if you see such kind of shape, okay, then it will be called as convex meniscus. It is completely flat. Okay. So in this topic, we are going to study the concept behind formation of such meniscus, whether it is concave or whether it is convex. Plus two more cases of angle of contact also, whether it will be 0 degree, whether it will be 90 degree, as well as acute, as well as obtuse. So in detail, we are going to study how all these things work. Okay, so let's understand the first case. This is nothing but a solid which is in contact with the liquid. This is the free surface of liquid. This liquid we are taking as a liquid which wets the solid. It could be kerosene, it could be normal water. Okay. Now, when this liquid molecules come in contact with the solid, definitely there are going to be adhesive forces, and those adhesive forces will act in the sphere of influence. So around this A point, I'll be drawing a sphere of influence. So let us consider this is your sphere of influence. Okay, so here I shall show all these adhesive forces. This all are the adhesive forces acting on molecule A. Now, so many adhesive forces, we are going to convert it into a single resultant force. So what I'll do, I'll just rub all these forces and I will convert it into a single force which will be acting. Okay, so let us consider this is that single force denoted by P. So AP is the resultant of all the adhesive forces acting on point A. Understood? Plus, we have cohesive forces also. This A molecule will be attracted by its own liquid molecules also. So similarly, I can draw lot many cohesive forces also. But I'll show it as a resultant, only one force. Let us consider this is that force which is denoted by C. Okay. Now, one important thing which you need to note is the adhesive forces are very stronger in case of a liquid which wets the solid. Okay, like water. So, in this case, the length of the arrow AP should be definitely more than the length of the arrow AC. This suggests that magnitude of AP, value of AP is more than value of AC. It means that resultant adhesive force is definitely more than cohesive force. And hence I am changing this. So the AP will be shown something like this. Clear? Now consider these two forces, okay, AP and AC. I need to draw a resultant of this two. Again, I need to draw a resultant of this two. So if I take you to a very simple concept, like we have one force P over here, second force Q over here, and I need to draw a resultant of this from the topic scalars and vectors, then resultant will be somewhere over here. Correct or not? So same way for these two forces, I am supposed to show a resultant force. So that resultant force will come somewhere around here. This will be denoted as R. That resultant force will always lie in the solid because inside solid adhesive forces are stronger. AP value is more. So resultant will also lie on that side. Okay. Now for stability of the liquid, let me tell you, this meniscus will remain perpendicular to this resultant force. I repeat, for stability of the liquid, the resultant, the meniscus of the liquid will remain perpendicular to this resultant. And hence, what is going to happen is this meniscus will rise. this meniscus will rise so that it becomes perpendicular to AR. And when I draw that tangent over here, this is the tangent, like it is perpendicular to AR. So I can say AT is perpendicular to AR, and here what I get is the angle of contact. Okay, so I'll just show it. This is angle theta. Okay, so the diagram has been completed. Now, just I'll make sure that this sphere of influence is not troubling a lot. Okay, so what does this conclude? In next diagram also we are going to apply the same logic. Okay, but this time I'll be not drawing sphere of influence always. We will draw AP, AC, AR, and then directly the tangent. And accordingly, we will get the meniscus shape as well as the angle of contact. Here you can see that meniscus shape has come as concave. It has risen. Okay, and when you see the angle of contact, it is coming as acute. Let's move on to the next part over here. In case of mercury, which is, does not wet the solid, cohesive forces are stronger and adhesive forces are weaker. So in this case, AP will be shown by a shorter arrow, whereas AC has to be shown by a longer arrow. This is your AC. Now again, we have to draw the resultant of this two. Since this is stronger, you can understand that resultant of this two will this time lie inside the liquid. So when I draw the resultant of this, it will be somewhere over here, AR. Got this? And as I told you, for stability of the liquid, what is going to happen? This meniscus will try to remain perpendicular to this resultant AR, and hence it drops downward like this. It drops downward. And we are just supposed to draw a tangent to this perpendicular to AR, which will be termed as AT, same way. And when you measure the angle inside the liquid, like I can see it over here, this is the angle theta. Got this? So what you can observe that meniscus in this case becomes convex, and the angle of contact is very well seen as theta. Let's move on to the next part, which is angle of contact equal to 0. Now, angle of contact can be 0 in case of pure water. Okay, in case of pure water, the angle of contact becomes 0. Now, let's understand why it becomes 0. In this section, wherever there is contact, okay, the molecules are very less in number. Liquid molecules are very less in number. So because of less liquid molecules, the cohesive forces are almost considered as 0. So here only adhesive forces will come into picture. So I'll be drawing only AP. Okay. So this is AP, no AC this time. Keep that in mind. Now if I ask you what is the resultant of this? Okay, like we were having AP, AC, and their resultant. Here we have only AP, only one force. So resultant of one force will be the same. So AP and AR is going to be the same in this case. Now you know what is going to happen for stability of the liquid. This meniscus will try to remain perpendicular to this resultant, and hence you can observe that it is straight away rising upward. It is straight away rising upward. We are just supposed to draw the tangent to this part. Let us consider this is our tangent, which is AT. Okay, and you can observe that surface of solid as well as AT, they are both in same line. They are parallel. So the angle of contact in this case will be equal to 0. Okay, so this is the case of pure water, where cohesive forces are taken as negligible. Okay, let's move on to the last part, 90-degree angle of contact. This is a hypothetical case which we are going to study. Okay, to have 90-degree as an angle of contact, you can understand that we need AR, resultant of AP and AC, to be along this surface of the solid. Okay, I'll show it on the diagram. Let us consider we have AP over here. This is AP, resultant of adhesive forces. Let us consider we have AC over here, which is resultant of cohesive forces, and our AR should come exactly along this surface of solid. This is our AR. Okay. Now, once AR has come over here, the meniscus of the liquid need not do anything. It is already perpendicular to this AR. I hope you can see. Okay. So we are just going to draw a tangent over here like this. Like it is perpendicular to AR, which will be denoted as AT. Okay. And this AT makes the angle with the surface, which is coming around as 90 degree. Okay, so in this case, the angle of contact will be equal to 90 degree. But when AR will come exactly along the surface of the solid, we need a condition for that. The condition for that is AP should be equal to AC divided by root 2. When such condition is achieved, then only AR will come along the line of the surface of solid. Clear with this? Similarly, if we go over here, then here we need AP. Here we need AP should be greater than AC by root 2. Then we will achieve this condition. And here AP should be less than AC by root 2. Then we will be achieving this condition. And here no case about AC, whatever AP is there, the same is AR. So this is how we complete a topic on shape of meniscus. Okay, so let's move on to the next topic, which is shape of liquids, liquid drops on a solid surface. I have drawn a diagram in which you can see that liquid is having a particular shape. Usually we have seen such kind of shape on our surface whenever we see it in our day-to-day life. But let me tell you, in case of mercury, the shape of the drop will not be this way. It will be completely different. So let's try to understand what is the logic behind that. Okay. Through this diagram, we are going to derive this formula, and you can see that T1, T2, and T3. Three things are involved in this. So let's understand what are those three things. You have heard of surface tension, which exists between solid and liquid, but in this case, we are going to consider surface tension between solid and air, as well as surface tension between the air and liquid interface also. So T1, it is the force of surface tension between liquid and solid, which we know. You can observe here, this is your liquid drop, this is your solid. So this is that surface tension between liquid and solid. Secondly, this is force of surface tension T2, which is between air and solid. So here we have solid, here we have air. So between this two, we have T2. And the last one, which is force of surface tension between air and liquid. So this is your liquid and this is your air. So the T3 is the surface tension force due to air and liquid. Okay. So let's proceed for this. What I'm going to do is I'm going to resolve this T3 into its two components, cos theta and sin theta. Correct? So you know that how to resolve it. The part where it makes an angle, T3 is making angle theta with the horizontal surface. So that part will be denoted as cos theta. So I'll write this as T3 cos theta. And perpendicular to that will become your sin theta. So this will be written as T3 sine theta. Okay. Now, for equilibrium of the drop, equilibrium means stability. It is stable. It is fixed. Now it will not change. For equilibrium of the drop, the forces should balance each other. Am I correct or not? So rightward force is to be balanced by leftward force. Okay. So on right hand side, which all force you can see? T1 plus T3 cos theta, and on left hand side you can see the force which is T2. So let me write over here, rightward force are balanced by leftward force. Okay, so now you can observe T3 cos theta can be written as T2 minus T1. So cos theta can be written as T1, sorry, T2 minus T1 upon T3. That is what we got over here. Now we are going to consider four cases involved in this. When will be the angle acute, when it will be obtuse. It can be obtained from this formula also. So let's move on to those four cases of angles possible. Okay. First case is, let us consider T2 greater than T1. Okay. So if T2 is greater than T1, then when you subtract this two value, obviously cos theta will come as positive. I hope you understand. Let us consider this value as 2, T1 as 1, 2 minus 1, 1, and divided by T3, let it be root 2. So 1 upon root 2, you got a positive value. So angle here in this case would be equal to 45 degrees. So ultimately, when T2 is greater than T1, I can write cos theta will be coming as positive, and therefore theta value will be coming acute. Like I gave you an example, it was coming as 45 degree. So I write this as acute. So now you will understand what are these cases all about. First case I have done. Let's move on to the second case. Now I will take T1 greater than T2. Means this value is greater. So if I consider this as 2 minus 3 upon root 2. So that will give me minus 1 by root 2. That is cos theta will be coming as negative. And when cos theta comes as negative, you know the angle for negative value of cos theta will be termed as obtuse. Okay, I'll give a simple example. Let's say I have cos 135 degree. So I'll be writing this as cos 90 plus 45. Cos pi by 2 plus theta. You know it will become sine theta. That is sine 45. And this lies in second quadrant. So this will be coming as negative because in second quadrant cos is negative. So since cos is negative, I need to give negative sign. So I got this as minus 1 by root 2. So whenever we have cos theta value as negative, definitely the angle is more than 90 degrees. That is how we come to this conclusion. Let's move on to the third case. Third case is T2 minus T1. Whatever value you get, okay, it is equal to T3. Understood this? So if this both values are equal, then it will get cancelled out. So answer will be 1. Okay. So therefore I can write cos theta is equal to 1, and you know that for theta equal to 0 degree. Okay. Cos 0 is 1. So in this case, theta value will come as 0 degree, 0 angle of contact. And one last case that we are going to study is T2 minus T1. The whole value is greater than T3. Okay. So let's say T2 minus T1 value is coming as 4. Okay. And T3 value is root 2. So 4 upon root 2, that is a huge value. It is not in the range of minus 1 and 1. So cos theta values, you know, it ranges from minus 1 till plus 1. Above 1, we don't have any value for cos theta. So in this case, the drop will never be formed. This is a hypothetical situation, okay, in which we will not be able to see a drop at all. Okay, so in this case, I will write drop is not formed. Clear? So this was the case of acute angle. Okay, for mercury, if I want to show this in a short, small diagram, I can show it like this. Here we have solid. Mercury will be having this kind of shape. Okay, it will be a sphere like where it will be contacting at only one point. Clear? This will be your T3, this will be your T3, this will be your T1, this will be your T2, okay, and here you can observe that angle of contact is obtuse. So this way we complete another topic regarding various shape of liquid drops. Let's move on to a very short theory topic about what are the factors affecting angle of contact. I have listed three factors. First is nature of liquid and solid in contact. Means if you have a particular liquid, let's say pure water, if you have a particular solid, let's say glass, and we have seen that in case of pure water, the angle of contact is coming as 0. Now, if you change the liquid, instead of water, if you have taken kerosene, then angle of contact will change. You can observe 0 and it becomes directly 16 degrees. Even if you have kept pure water and if you are changing the material, okay, solid if you are changing, then there could be slight change in the angle of contact as well. In case of normal water, you can observe that instead of glass, if you are taking paraffin, then the angle of contact is directly becoming 107 degree. In case of mercury also, you can observe that angle of contact value is completely changed. It is something around 140 degree Celsius. Okay, so liquid and solid pair changes and the angle of contact also changes. Let's move on to the second part, which is impurities. Impurities, adding impurities does change angle of contact. We are going to study effect of impurities in detail. You can observe that if we add a soluble impurity like NaCl, okay, then surface tension, okay, of that liquid will increase. Angle of contact do change, but at the same time we are considering surface tension also. Adding soluble impurity increases the surface tension. Let's talk about second impurity, which is sparingly soluble, not completely soluble. To some extent, it is soluble. The example given is phenol and or detergent. So surface tension decreases. I already told you in our previous lecture that detergent decreases surface tension, and because of decreasing surface tension, the water molecules are free. Cohesive forces are reduced to a lot extent, and water molecules can reach the corners of the clothes where stains are present and can remove the stains. Okay. Let's move on to the next, which is insoluble impurity. Okay, then in that case also the surface tension decreases. A simple example is given. If you add dust to mercury, okay, then surface tension is definitely going to decrease and it won't be able to form the droplets so easily. Okay, now we move on to the third factor, which is affecting angle of contact, which is the temperature of the liquid. From this relation, you can easily make out that this is temperature. Let me tell you, this is not surface tension. Here it was surface tension, but here it is temperature. So temperature is inversely proportional to angle of contact. If you increase the temperature, angle of contact will decrease. Again, let's link this temperature with surface tension also. In case of temperature increase, the surface tension decreases. Okay, I'll give you one example. Like if you are being asked to wash clothes, which water will you prefer, cold or hot. Usually we will prefer hot water, but there is a very interesting fact to prefer cold water also at times. Okay, so let us consider if we have a new cotton fabric, okay, very new, whose color is quite attractive, okay, and we don't want to make that color of the fabric to be dim, okay. So in that case, it's better to use the cold water because cold water means less temperature, and less temperature means more surface tension. So water molecules will not touch the fabric a lot extent, and it will not remove the color. So color would remain as it is for few wash. Okay, so I have written it for new cotton fabric. Cold water is preferable because it does not lose color. Whereas in case of hot water, you can observe that surface tension will decrease, cohesive forces will decrease, and waters can reach the corners, and it will be helpful in removing the stains. So this was a short topic, theory topic regarding factors affecting angle of contact as well as factors affecting surface tension also. Thank you.